the upcoming course, what we are going to do in these 2 days is to kind of give you a little taste of what is going to be over 30 hours. Now, there is 2 aspects to this particular course. One is the understanding of statistics and how that pertains to applications in geosciences, and the coding aspect itself. So one of the assumptions that we would go into the course is that everybody here knows how to write basic Python code or are familiar with the syntaxes. Now, that would be one of the requirements. You do not need to know any kind of statistics, but if you are not aware, if you're a pure beginner in Python, you would have to work a little hard, because the first day I might do some background information, but that would be essentially a Q&A. So today and tomorrow would be your best time to kind of catch me on Python related issues and topics. And then the main course will essentially focus on understanding the statistics and how we can write Python code to solve those statistical problems. Now, let us take a step back and think in terms of what do you mean application of statistics in geology. Now, let me give you a very simple example. Let's say you are a mining company and you are interested in developing some sort of a mine plan before you start digging up the land, or you buy the land for mining. Okay, and that part typically is called exploration. And during your exploration phase, you have collected a bunch of data. Obviously, these are drill data, hand samples, soil samples, could be all kinds of samples. And based off of this data, you want to have an idea, what is the orientation of the ore body? Okay, or is it the same rock unit that I am seeing? So for example, you are in location A and you have collected a hand sample, and then you have collected another hand sample from location B. Both of them happen to be pegmatites. Now, if you can somehow demonstrate that these 2 pegmatites are the same body, then you could essentially map it together as one body of pegmatite, and perhaps you are looking for pegmatite to extract quartz for, whatever purposes, like abrasives, or if it's a high quality pegmatite, then you are probably going to use that for silicon chips and so on and so forth. So it depends on your end result. Essentially, you are interested in it. Now, what are our available tools to indicate that either things are similar or different? And physical examination is not enough. When you are talking about a company making profits and so on, you want some quantitative proof. Now, the question is, what do you mean by quantitative proof? Well, what we can do is take a bunch of samples from location A and a bunch of samples from location B, and then we can compare them using what is called certain statistical procedures. And then we can provide what is called an uncertainty value as to how confident you are that they are the same or they are different. Okay, so that you are not just merely depending upon the chemical analysis and saying, well, if they are not exactly identical, you have no way of saying they are same. But we know in geology that natural variation is very common. So is there a way to kind of weigh into that this is same or different? The answer is yes. The answer is statistics. Now, in the main course, we will actually discuss and define definitions. There is no point me explaining concepts in these 2 days, because this is too short for you to wrap your head around that and understand the application. At least that's the way I have planned the course, that I don't want to start talking about big concepts in statistics as applied to statistical tests and so on and so forth. So what I want to do here is show you some fun skills with what you can do, particularly as far as generating some figure plots are concerned and handling some data. So essentially refresh your Python memory, and in the meantime show you what kind of statistical things we would do. I am going to actually work with some data from collected from a volcanic area, and do some basic statistics, some linear regression, and one example of a specific how to set up statistical hypotheses. Okay, so these are my 3 goals for the next 2 days. If we have time, I'll add something up. So, and in the meantime, I'm happy to take questions and things like that tomorrow. But if there is some simple clarification, please feel free to stop me and ask. Okay, so what I have open in front of you is called an IDE. You probably know that, which is an integrated development environment. That's a fancy way of saying that this is where I would write the Python code, and some values are going to show up, and we are going to get some results, and we will see that. All right. So give me 2 seconds to kind of set up the, set things up, because I have to move some data. Yes. Today is 13/5/20. All right. So I have essentially created a file, a Python file, where I'm going to write some code. Now, what I'm going to use is a particular data set, and I will show you that data set. So give me a second. I want to show that data set to you. Find the code. So that you understand what I am going to do with this. So this data set contains several the analyses, the chemical analysis of several volcanic layers, and we have major element analysis. We have trace element analysis, and we can do different types of statistical tests with that. So thank you for your patience as I wait for Excel to open up on my computer. Well, as the thing is opening up, let me start writing some fundamental code as far as looking at performing some descriptive statistics. So in this particular case, I'm going to write a comment, descriptive statistics of volcanic data. Okay. Now, if you have forgotten what this descriptive statistics is, it entails the statistical procedures that describes the data. Okay, describes certain parameters of the data. Okay, and what are they? So the very simple descriptive statistics are mean, median, mode, standard deviation, variance, and so on. These are our primary descriptive statistics. Okay, and oftentimes we use a range. Obviously, range is another one. A max, min, so on and so forth. So they essentially tell you certain things about the data. They describe the data to you. So for example, the mean is supposed to tell you that what is the representative average of this data set. All right. The median and mode similarly talk about the central tendency. So the mean, median, mode fall under a fancier term called central tendency. And then, what is that called? Variance and standard deviation, they fall under what is called dispersion. That means what is the distribution of the data relative to the central tendency of that data. All right. Now, another thing that I want to add to here is, can we perform statistics willy-nilly on any data? What is the fundamental underpinning of the statistical tests? And during the course, we will, in a very long-winded way, demonstrate to you that we start with the idea of randomness. We assume that whatever is happening randomly, and one occurrence does not control the other. All right. And based off of that, there is an amount of mathematics that has been developed by statisticians and mathematicians that indicate what happens as we deviate from this randomness, from pure randomness or pure chaos, into some sort of an order. Because pure randomness or pure chaos is extremely difficult or absolutely impossible to characterize mathematically. Okay. So, but in nature, we have observed that there is a mixture of order and disorder in the data. Okay, as well as in the natural phenomena, which allows us to perform these mathematical gymnastics to be able to extract information from that data. All right. Now, my Excel has opened up, so allow me to show you the data. Share. So over here, what we have is an analysis number. There is a large number of analysis over here. And if I scroll all the way down, you will see I have something around 371 analyses of different samples. And then this particular data set has a lot of information, but the key part is over here, which is the part that is moving. So you can see that I have the bulk composition of SiO2, then this trace element data, scandium, rubidium, strontium, ytterbium, and so on and so forth. Okay, for all these samples. And it is entirely possible for us to understand how a particular rare earth element is behaving, because the behavior of rare earth elements actually tells us about the mechanism of the igneous process through which the volcano had actually gone through. And so we are interested actually in the evaluation of this kind of a data. Okay. Now, in the actual course, we will spend some time working with this type of data, but we will also consider other types of data. Like, for example, we might look at paleontological samples collected from two different areas and try to figure out if they are the same or they are different. Then we can look at the calcium oxide concentration of limestone in different areas and try to figure out if this is the same limestone bed or not, again, from a mining perspective, and so on. So again, all of the examples that we will be showing during that particular course are directly related to geology and exploration geology. And then all the statistical applications are obviously on that geological data set. All right. Now, allow me to show you some basic figure development in this particular session. All right. So I want to look at some very simple statistics. In fact, the first thing that I'm going to do is generate the mean values of a data set. And specifically, I want to look at the distribution of zircon. Okay. And then what I'm going to do is then focus on trying to understand another concept called probability. Okay. And then we will discuss how that is done. Again, I'm not going to go into the detailed description of that, again, because this is more of a show and tell. All right. Now, because I have an Excel spreadsheet, the easiest way to extract data from Excel in Python is pandas. All right. So what I'm going to do, hopefully you can see my screen completely, the coding screen. And so what I'm going to do is I am going to import certain libraries. Okay. So I'm going to import pandas as PD. Then I am going to import a statistics library called SciPy. And what I'm doing here is essentially from the statistics library, I am importing two specific means. One is called the geometric mean and other one is called harmonic mean. And obviously our good old friend arithmetic mean is also there. But we will, for the arithmetic mean, we have a direct command to do that. Okay. Now you would say, well, why am I bothering to show you geometric mean and harmonic mean? If some compared to our regular arithmetic mean. If somebody knows the answer, they are more than welcome to write in the chat. Why am I trying to show you harmonic mean and geometric mean? I will continue to write the code in the interest of time. So what I have done is this is for data analysis, the pandas, statistics is for these, and matplotlib is for plotting. Okay. And so what I'm going to do is I'm going to say that my data set, I'm going to save it as a pandas file. Okay. And so I'll ask it to read this pd dot Excel. Excel was X. All right. So essentially what I'm saying is that read an Excel file, and this is the name of the Excel file. Now, this particular Excel file happens to have more than one sheet. So I can specify the sheet name. All right. And the way I do that is say sheet underscore name equals, and then I say the name of the sheet. Traces. Okay. I close that. And then I close that. Okay. So this is where I have extracted the data. Okay, or I've asked the system to extract the data. Excellent. Now, what's next? Now I am going to, so let me write some comments. Extracting data into pandas data frame. Again, if you don't know what a data frame is, don't worry about it. It's an XY grid. It's essentially like a spreadsheet, and we'll explain that later, perhaps tomorrow when you have more questions for me. And so now I'm going to do some calculations. Calculating mean or A mean, which is arithmetic mean, G mean, H mean. Okay. And so this is actually pretty straightforward. I can say A underscore mean equals, and all I have to do is say what is my data set, which is DF. DF is my data set. Then in my data set, I have the column name under which I am more interested in is zircon. And then all I say is mean. Okay. And that's it. That's all I have to do. Again, I will have this printed out separately. So actually, I'm going to make it pretty straightforward and have it printed out right away. Say print A mean. Okay. Next, I will calculate the geometric mean. And again, I'll do the same thing. But this time, what I'll do is I'll do things the other way around. Because standard Python doesn't have a function for geometric mean. So I will essentially extract the geometric mean from here. So anybody still have any idea as to the answer to my question that I had originally asked, why I am doing geometric mean and harmonic mean? Okay. So then I can then again say this as data frame and then the column. So that these are two ways of looking at, see how I have done it here versus how I have done it here. And then obviously I'll have this printed out. Then H mean, oops, sorry, could be H mean, then DF, that. All right. Now, that is all nice and good. Okay. And in fact, I am done. I mean, I'm done writing code. Okay. As far as calculation is concerned, Now, this would be overly simplistic. Obviously, you are not going to be interested in joining a course if the coding is this simple. It is not. I'm going to do a lot more coding to show you the plots and things like that. But this also indicates that it is so easy to quickly calculate these means. So if I run this code, it will take a little time to import these different libraries, read the data. But once that is done, these values are going to show up immediately. So you unfortunately have to be a little patient because my computer is an old one. So it sort of trudges along a little slowly. And it's already a Saturday night. So I typically give my computer Saturdays and Sundays off because it needs rest as well. But I guess I was being too insulting to it. So it has essentially generated the mean values and given it to me. Now, I haven't calculated the harmonic mean. So let me print that as well. Okay. And now if I execute this again, this should run relatively quickly. All right. So you have these values. Now, I am not going to show formatting stuff here today because it's a kind of, one assumes you know that. If you don't, again, we'll discuss it tomorrow. Now comes the plotting, and this is the fun part, and this is what everybody wants, because you would be able to take that plot in PDF and essentially put it in your article or report or whatever it is that you are trying to develop. Okay, so we are going to plot these values. Okay, so what are we going to plot? So we are going to plot a histogram of zircon. Okay, and this histogram of zircon will be done, and this would be zircon versus probability density. Now, what is probability density? Don't worry about it now. All of that will be explained in the course itself. So let us write that part of the code. So, and that part of the code goes something like this. So I'm essentially saying I'm going to create a plot, and then I'm going to say AX dot hist means histogram. Now you would say, how do I know that AX dot hist is histogram? Well, again, that is the assumption that you are familiar with Python, but you know, this is where this comes from matplotlib or the plotting library. And how do I know that? Because it's right here. plt.subplots is saved in figure and AX. AX is the axis on which the work is being done. So I'm going to create a histogram. Now, to create a histogram, obviously, I need two data, but I have to provide whatever is in the x-axis versus whatever is in the y-axis. So I write this as that. Then bins equal auto. Now, you would ask the question, well, hang on, what is these bins? Well, you know what a histogram is. You have to kind of say a range of values. So in a histogram, what you do is you look at all the values and kind of put them into different buckets or different value ranges. So I am giving the control over to the program to do that. And then I'm saying that I want a probability density distribution of that. What do you call that? The bar of the histogram, I want the edges of that to have the black. You can choose whatever color you want. Then what I'm going to do is I want to create some labels as well. And I also want some transparency to the thing. All right. The next thing that I'm going to do is, so let me write this. Figure, generate histogram, generated the histogram. And the next thing that I'm going to do is I am going to mark the different means. Mark the mean values on the histogram. Why? Because then you can actually see the spread of the data. Okay. So let's do that. And so what can we do here? And so for that, what I'm going to do is create some vertical lines that will do that. Ax dot ax v line, and then I say a underscore mean color equals purple, label equals this one will be arithmetic mean. I'll say that the line width is equal to 2. Okay. So how thick that line is going to be. Now, I'm going to copy this and repeat this for the other two as well. Now, and then what I'm going to do is go back here and change this to G mean, H mean, change the purple to, I don't know, orange, orange, and this could be green, perhaps. Okay. Then this would be geometric. Then this would be yeah. So essentially, I've written all the commands I need to write to generate those. Now, obviously, I have to provide some labels for the axis labels. I have to create some axis labels. So I'm going to say ax dot set underscore x label. And then I would say that it would be zircon in ppm. Close this, and then I say ax dot set underscore y label, and this one I'd say, oops, sorry, probability density. All right. Now I will also create a legend. And then all I would do is show. Okay. Now, if I do that, we'll see if this works or not. So I'm going to save this and I'm going to run this. Okay. Now, you probably are not able to see the plot. So I'm going to show you the plot. Okay. So this is what the plot looks like. Now, the advantage of this code is it doesn't matter how many data sets you have, as long as the data set's format is the same. It doesn't matter how many projects, how many analyses you have. All you have to do is run this code and change just the file name from which the data is going to be extracted. Okay. Now, one of the really cool things about this is obviously you can see up on the top, I can kind of see the value coordinates are changing. So this is the probability density, and this is the values of the zircon over here, and you have your different mean values plotted. Now you would say, well, yeah, but what about the other ones? What about the median and all of that other stuff? Well, let's add them. It's not that hard. Now, you might want to save this. Now, one of the things that you can do is save it from here, which is save the figure. Now, if I save it from here, let's see what are the options I get. The options that you get are typical, and one of the option is PDF. Okay. Now, there are other options as well, but which is awesome. You can save it as PGF code for LaTeX. You can as JPEG. Then you can encapsulated PostScript, PNG, TIFF, whatever. So you can have all these different varieties. Now, the advantage of saving it as a PDF is that you get a very high quality PDF figure that you can save. Now, if you remember, I'm not going to save this. If you remember from your coding experience, now let me go back to the code. It is possible for you to save the document from inside it, the code itself. Okay. And let me see. It's plt.savefig, and then you can put in the DPI of the PDF as well. Okay, so one of the things that you could write is plt.save_fig. Then, you know, I don't know, you know, fig.1 or figure1.pdf. Then you would say DPI equals 720. Okay. Now, the result would be essentially that your file name would be fig1. It is going to be a PDF file, and the DPI is going to be this. So, you know, if you want a quick low resolution picture, you can also make this something like that. Okay. Or 300 DPI, or, you know, it's absolutely up to you. Okay. I'm going to comment this out because I don't need that. All right. So let's put in the other stuff. You know, let's put in the median, mode, and all of that other stuff. So what I'm going to do is calculate median and mode. Okay. Now, to do that, what are we going to do? Now, for median and mode, for mode, we have to be particularly careful because we have to do certain things. Now, let's say I'm going to write this as median equals df dot zr dot median. Okay. Now, that's how we can do median. And again, we can also then print the median, print median. And then we can add that median stuff here as well and say, mark the mean values. So now I'm going to add the mode value as well. And how do I do that? I'd say ax dot ax v line, and say en comma color equals red, label equals median, line width equals 2. Okay. So again, I can quickly generate that. No big deal. Now let me do the mode as well, and then I'll stop and take questions if you have them, and then go from there. All right, now let's look at this. Now, for this particular one, we have to write an additional piece of code. Okay. Yes. So for mode, no, let me do this as separate. Yes. Mode. Then we go mode. So for calculating the mode, I have to do a couple of things. And yeah, that would be list comma in edges. Now, if you remember, mode has to be, has to be calculated between the bins. So I have to first calculate how many bins are there and then plot it. So that's why I have to do some other manipulation. And in fact, that is why I have to import another library. Okay. That is equal to np.histogram if dot comma bins equal 20. Oops, density equals true. All right. And from this, I'm going to calculate the modal value. Okay. So I'm going to say modal value is equal to again, this is an equation that is well known. And so we are just using ist dot argmax plus edges ist dot plus 1 this thing divided by 2. All right. Or in other words, what we are doing is we are finding the maximum and the minimum, adding them up. We are finding the argmax and argmax plus 1, and then dividing it by 2 to get the mode. Okay. Now, as far as the calculation is concerned, that is done. All I have to do is print that. All right. Now I have to do the same thing. And this would be model underscore value color equals blue. Oops. Then label equals mode line with equals. Okay. And that's it. You're done. And it doesn't matter if this is your PhD, if this is your master's, if this is your class report, if this is for a journal article, if this is for your job, if this is for whatever. Okay. And you are done. And if I execute this code, okay, so I guess I made unless I made a mistake somewhere, we will find out how this goes. Okay, so there was no mistake. So let me show you the plot. Okay, so there is the plot. In fact, you have a nice graph which has an x-axis spelled out, a y-axis spelled out, and then the different values. Okay, and you can see the modal value is over here, the median value, the harmonic mean. Now, you might say, well, hang on a second, it would be so much nicer if the actual value is put in there. Now, that is also possible. That is not a problem. It is perfectly, it is very simple to actually put in the value itself over there. Okay. And so you might say, well, how would that be? Now, well, let's try that. Let's try that. Well, if it doesn't work, it doesn't work. Now, there are little things that I am doing. Again, that we would have more time explaining all of that while we are in the course. It's very difficult to kind of go through that on a workshop when I'm trying to kind of show you the things that we can do. All right. Let me share that with you. Now, I was not very careful, and I apologize for that. You can see your arithmetic mean, your geometric mean. Now, the value is also here in addition to a pictorial representation. Now, you can see this kind of looks very ugly. Okay. Now, that is also very easy to solve because, I only want to see only 2 digits after that. That is not a problem. That's very easy to solve. Again, those would be the things that we can look at during the actual course, where we can go into the nitty-gritties and finer things of that. All right. So this would be something that we would also do instead of doing this with Zircon. I will actually provide you with several data sets where you are to generate these kinds of plots from the very get-go. and do certain analyses and then draw certain interpretations and conclusions. Because at the end of the day, just doing statistics for the sake of statistics is, no fun. You actually want to be able to say something meaningful. Now, I asked a question a while back about why we were looking at harmonic mean, geometric mean, and all this other stuff compared to arithmetic mean. Now, if you look at the arithmetic mean value here compared to the other means, at least if you look at geometric mean, harmonic mean, and the median, you will see all of those bunch up together close to each other. Whereas the arithmetic mean is kind of shifting away from those. And the reason for that is you can see in this particular histogram or this distribution of zircon concentrations that there are some bins that contain large values. And the large values or outliers attract the arithmetic mean. Arithmetic mean is very quickly influenced by outliers, whereas the geometric mean and the harmonic mean are not so influenced by that. Now, you would say, well, why do I care about that? Well, the reason you care about that is you want to have a firm understanding of what is the true central tendency of that particular unit. Because then when you try to understand dispersion, when you try to calculate the standard deviation and variances and so on and so forth, you have a much more solid standard position to measure off of. Okay, it's akin to saying you know what is the mass of 1 kilogram. That is why we can measure 10 kilogram, 20 kilogram, 30 kilogram, 40 kilogram, whatever. But if the mass of 1 kilogram is sort of nebulous and is kind of, you can shift it around, all the other measurements that you are doing have an inherent error that gets inbuilt into it and makes the analysis more complicated. All right. I'm going to stop talking here and